Hey everybody, welcome to Amazon. Today we are going to do an analysis of capacitor dropper circuits. This is the circuit that we usually see in bulbs in our households. This supply is used whenever there is a requirement of low currents. Now, why we use this circuit? First of all, this circuit gives us the advantage of the cheap components, and to build this circuit, the cost is very low. The second is with few components you can drive any low level circuits, low current circuits easily instead of using a transformer circuit or let's say SMPS. Though SMPS is highly recommendable, but it cannot be used everywhere because the cost of the SMPS is more compared to this transformerless power supply. Now let's go deep dive into the capacitor dropper circuit. No, this is the basic circuit that is usually used in transformerless power supply. There is a capacitor dropper circuit that is C1, that is R1 resistor, there is a bridge, Zener diode, capacitor to remove the output ripples, and finally the load that we want to drive. There is also one R2 resistor which is used to limit the inrush current. We will go through each and every part of this in the video ahead. Now, let's just point out the specification that we need for our circuit to be built. See, input supply would be 230 volt AC that is usually used in India. It can vary from 195 volt to from 265 volt AC. So it will be around 260 peak to 390 or 375 peak. We want an output supply of 5 volt DC. Now output current of an LED for maximum that we can see from the data sheet or we obtain from the data sheet is about 30 milliampere. So we don't want to design our circuit for the LED to go to consume more than 30 milliampere or even close to 30 milliampere. So let's just say that we want an output current of 23 milliampere. This is just an assumption. There is no rule you can take 20 milliampere, 10 milliampere. It is according to your requirement. Depending upon the current, there will be intensity. If you use small currents, then intensity will be low. And if you use large currents, then there will be high intensity. Another thing that we need to see from the data sheet is the voltage drop across the LED. That is 3 volt, meaning there will be 3 voltage drop across the LED to light up the LED. Now these are the specifications. Now for a transformer to build a transformer power supply, it basically or typically incorporates rectification, voltage division, regulation, filtering, and industrial limiting. We will see all these topics here. Now, before diving deep into this, the transformer power supply is typically a voltage divider circuit, but not a resistive voltage divider. It is a capacitor voltage divider circuit. Instead of using two resistors to drop down the voltage, a capacitor it is used, and it is highly more advantageous than resistive dropper circuits. If we use resistive dropper circuits, then there will be a power drop and heat will be dissipated from both the resistors. And usually, most of our power will be lost in the resistor which we are not going to use. But in capacitor, if we use capacitor, then there is no loss of heat in the capacitor as capacitor is does not consume more power. It has an imaginary power. So let's say voltage before the bridge. It means that we want 5.1 volt here. Therefore, the voltage here would be around 5 volt. How? 5.1 volt. This is the peak value. Now we have to convert into RMS. Then 5.1 volt divided by 1.414, that is 3.61, and the two voltage drop circuit that we are going to drop across the diode, it is for one diode it is zero point 0.7 volt. Now for two diode it will be 1.4 volt. Therefore 5.1 volt will be across here. Now as you can see 230 volt minus 5 volt, we want the capacitor to hold the 230 minus 5 volt, that is to 25 volt, to be held across the capacitor. So now voltage across the capacitor is 230 minus 5 volt is equal to 225 volt. Now the current that we require is 23 million. So we can calculate the impedance across the capacitor that is required. And this will be used as the maximum current that can be passed through the capacitor. Now Xc is equal to 225. Xc is the impedance of the capacitor. That is 225 divided by 23 milliampere, which gives the around 9.78 kilo ohms. Now, as we all know that the impedance is equal to 1 by 2 pi Fc, we can calculate the capacitance value, and the capacitor value will come across 325.59 nanofarad, which is usually congruent to 330 nanofarad that is usually available in the market. Now, this capacitor should be excited capacitor, which usually comes in red color, orange color, or green color. And as you know that the voltage rating should be more than 400 volt, because the maximum VRMS voltage that is going to be applied here is 265 volt, and the peak voltage will be 265 multiplied by 1.414, that usually comes across 375 volt. So it is safe to use a capacitor of 330 nanofarad that has a voltage rating of 400 voltage. Now, as we have calculated the capacitor value, that is 330 nanofarad. Now, the capacitor that we are going to keep at the output of the bridge rectifier to smooth out the ripple is the C2 capacitor. Now, to calculate the value of the capacitor that we are going to place is by the formula, that is C to is equal to IT by V. This is a famous equation which is usually used to uh, measure or decide which capacitor to be used in the as an output capacitor. Now, as you know that we are going to get 5.1 volt, and its peak voltage will be around 7.2 volt. Now, let's say that our voltage is uh, let's say for the rising edge our capacitor would be charged. But what about when when the shape of wave or the voltage is going to decrease and going to be in the negative half cycle? It's okay that it is not going to be in the negative half cycle because we're using full wave bridge rectifier, so it doesn't matter. But what about the falling edge of the wave? That is, let's say that our frequency is around 50 hertz. So the time would be around 20 milliseconds of the wave. So for 10 milliseconds, it is going to have a positive edge, positive wave, and for the another 10 seconds, it is going to have the negative wave. But as we are just using a full bridge rectifier, the negative wave will be converted to positive, and the frequency that we are going to use, usually we get is across 10 milliseconds. Then not 10 milliseconds, but it is the time that is 10 milliseconds. So for 5 milliseconds, our wave will be or the capacitor will be get charged. But after the wave reaches to the 90 degree, that is the highest peak, then the capacitor has to supply to the load. So as you know that we are going to get 5.1 volt VRMS. Now to convert it into peak, that is multiplied by root 2, that is 1.414, we will get 7.2 volt. So using the famous equation C2 is equal to IT divided by V. Now the current will be across 10 milliampere, let's say, and if the load requires it's 10 milliampere. For hour it is 23 milliampere. But just let's take a sample or an example. And the time required for the capacitor to give or supply the voltage would be around 5 milliseconds. First, let's say that we are going to use 10 milliseconds only. So it is safe to use that the capacitor is going to supply. If there is a difference, then the voltage will be supplied through the input and the capacitor will get charged. But otherwise, capacitor will be charged and all the voltage will be supplied to the load. Now, the V here is the difference that we are going to get. Let's say that the our V peak is 7.2 volt minus 5.51 volt. That is, we are requiring 5.1 volt as a constant, and it will be there as the zener is regulating the voltage. So we will get around 100 microfarad divided by 2.1 volt. That is around 47 microfarad, and this should be rated around more than 25 volt. The capacitor should be rated of 25 volt. In our circuit, we have used 100 microfarad, which is very safe to use. But using 1000 microfarad, it is easy and safe to use. But again, the cost will be high for 1000 microfarad capacitor. Now, the another thing to keep in mind is that to make an LED driver. Now our LED is going to consume 3 volt LED. Now the extra 2 volt drop has to be dropped elsewhere, or otherwise the LED will be blown up. So let's say that we need a bias resistor or the driver resistor so to protect the LED. Now the voltage of the bias that we are going to drop across the resistor is around 5.1 minus 3 is equal to 2.1 volt. And we also want to limit the current across the LED at around 10 milliamp. Let's just say that. Therefore, R3 bias is equal to 2.1 divided by 10 milliampere, that we are going to get 200 ohms. And we have used 220 ohms in our circuit as it is readily available in the market. You can get 200 ohms, but as I was having a 220 ohms in my lab, so I have used 220 ohms. Another and the most important part of building this circuit is the inrush limiting. Now let's say that when we switch the circuit or apply 230 volt, then capacitor is fully discharged. So it will act as a short circuit. Now all the 230 volt are for the first half wave. This is we are considering as a first half wave. No voltage will be dropped here, and it as it gives a low current path or a low resistance path, all the current will flow through this. Then it will pass through the voltage or the bridge rectifier, and then again it will pass through this capacitor, as this capacitor is also not charged, and it will act as a short circuit. Now all the voltage, and then if we do not put the resistor here, then what will be the condition? This is short, then let's say that live and neutral gas short, and there will be some resistance because of the bridge rectifier, but it is very negligible, and you may blow up the circuit very easily. Though the induced current will be for a few milliseconds or microseconds, but it can damage our the precious load. So to protect our circuit from inrush current, we are usually using R2 capacitor. And to calculate that, let's say that our socket or the 230 volt socket is capable of delivering 5 ampere current maximum or 15 ampere. Then and the voltage peak that we are going to get from the supply is 375. Then the resistance that we need to calculate, or the maximum or the minimum resistance that we can use to limit the current, is across that 375 divided by 5 that is 75 ohm. You should not use less than this resistance. To know that there is a trade-off in the capacity transformerless power supplies. We should not use a resistor too high because there will be a drop across the resistor, and it should be not as small as possible so that it gets less than this value, that is 75 ohm. Now, as we know that there will be an inrush for only first or for first 5 cycles. After that, the capacitor, that is the X2 capacitor, will be get fully charged. And as you know that the time constant for capacitor to be gets charged, or the impedance that is going to build up here, will take across 5 tau. That is 5 time constants. After that, we do not need this resistors, as it will get the current will be limited from this only. Now, as we know that we are going, let's say we are going to build a transformer power supply that is gives us our maximum output current of 30 milliampere because of the capacitor, the X2 capacitor that we are going to use. Then, if we use R1 resistor 75 ohm and for 5 ampere max induced current, it will generate a 0.0675 watt of heat or the power. So it is safely to use a quarter watt resistor across as quarter watt resistor as R2. Sorry, this will be R2. And let's say while inverse current will be limited to, and let's say if in our circuit we have used 100 ohm and 30 milliampere, we will get the maximum current, then it will just generate 0.09 watt of heat. So we can safely use a quarter watt resistor, and still it will protect the circuit from high inverse current. Another thing to remember is that this transformer power supply is non-isolated uh, supply or supply circuit. So when let's say the capacitor gets charged, and after some time you switch off the voltage, and there is no R1 resistor, then the capacitor will remain fully charged. And if you just touch at the capacitor, you will get a shock of 375 volt as the capacitor, or 225 volt as the capacitor is going to charge. So it R1 is used to quickly discharge the capacitor after the circuit has been disconnected, or 230 volt is not given to the circuit. Now the value of R1 should be as high as possible, because if we use a resistor that is very low in kilo ohms, then as we all know that after the capacitor is going to charge, it will be around it will give an impedance of 9 kilo ohm. And if we use a iron resistor is 10 kilo ohm, then typically this combination of two impedances or parallel impedances is going to be 5 kilo ohm. To avoid that, or to keep the capacitance as near to as 9 kilo ohm that we have calculated, to drop a 225 volt across this capacitor, we are going to use R1 resistor, which is mainly 1,000 times more than this value. Now, usually we are going to use 1 mega ohm resistance, and it will typically suffice. And we can also calculate the time constant that it will going to discharge is 330 nanofarad across 1 mega ohm, which will be around 330 nanometer, that is going to give milliseconds, and the capacitor will be discharged totally discharged if the supply is let's say disconnected, then the capacitor will be discharged after 5 time constant, that is cross 330 milliseconds, which will give roughly from 0.65 seconds. So after basically 2 seconds, our X2 capacitor will greatly be discharged, and if anyone tries to touch, then they will not get a huge shock. Usually, this circuit is used in an uh, enclosed body or enclosed box, because as this is non-isolated, there are high chances that even for a millisecond or microsecond you can get across a high voltage. So now we get to design, and I have explained all the necessary things to apply to build a transformerless power supply. So the capacitor V1 or C1 that we are going to use, that is X2 capacitor, is 313 nanofarad 400 volt rated. The capacitor C2, that is across this, it is 100 microfarad, and it I am going to use this 50 volt. RC will be 200 ohm, or basically as I have explained that I have used 220 ohm resistor, and R2, the induced current limiter, that is 100 ohm we are going to use, and it is safe to use. Remember in mind, I have used this R2 capacitor as 100 ohm 2 watt in our circuit. You can use 0.25 volt as we are not going to get, or it is going, because for a minute second it is not going to damage the capacitor, or sorry, the resistor for a minute second. But to be at a safe side, we are going to use a 2 volt resistor. Now, the bridge that I'm going to use is full bridge rectifier, and you can use a MB10F that is usually available in the market in the SMD version, or else you can use 1N4007 diodes that are capable or handling 1000 volts of supply current through it. We are using R1 as 1 mega ohm, that is for quickly discharging the X2 capacitor. There might be a need that we want to discharge this capacitance also, but as it is a low voltage and you are going to charge a 5.1 volt, this will be quickly discharged through this path, and so there is no requirement of using this extra biasing resistor here. That's it for it, guys. In the next video I'm going to practically display or give or make a video of I have built a circuit of these values that I have just shown here. Till then, okay, bye bye.